Calculus, video 21, the derivative of an exponential base e, or the derivative of the function e to the x. So a couple of rules just to remind ourselves that we already know. We have so far the constant rule. The derivative of a constant is equal to 0. You'll note that I'm using our new notation that we learned, right? D dx of a number, or d dx of a function. That means the derivative function. So the derivative of our constant is equal to 0, of any constant. And in the power rule, we see here the derivative, again, d over dx means the derivative of x to the n is equal to n times x to the n minus 1. Or you could also think about the power rule like this. The derivative of some constant times x to the n is equal to that constant times that exponent n times x to the n minus 1. And oftentimes that's how I think of the power rule, to have that constant out front, because most of the time you have a constant in front of your x base there. Okay, today we are going to look at e, the number e. E is approximately equal to 2.718281828 4, 5, 9, so far and so forth. For us, it's enough to think of e as approximately 2.72, 2.71, 2.72, something like that. Some number a little bit less than 3. But e, a lot like pi, right? Pi has been really important for us in mathematics, approximately equal to 3.14. E is similar to pi in that it ends up showing up a lot in mathematics and physics and engineering, right? A lot of places end up using this number e. It becomes really important in math. More important maybe even than pi itself. So we'll do a lot with e. And one of the reasons why it ends up being so important is for the following reason. Consider the function y equals e to the x. Hopefully we know how to draw y equals e to the x, right? It has the horizontal asymptote like this, meaning as x goes off to negative infinity, e to the negative infinity becomes very small. We know it looks kind of like this, small over here, then it kind of grows, because we say it grows exponentially. It passes through the point 0, 1, because anything to the 0 exponent is 1, so e to the 0 is 1. As x is very large negatively, it gets close to 0. As x is large positively, it goes up to infinity. So this is the graph of e to the x. And the kind of really important part about e to the x is this feature here. For some value a, the function value is f of a. But also, the tangent line at a. Alright, so here's a tangent line. The slope of that tangent line, remember the slope is given by f prime of a. The slope of the tangent line at any point on the function e to the x is equal to, the slope of the tangent line is equal to the y value at that same point. That ends up being really important. For e to the x, and maybe I'll write for f of x equals e to the x. For f of x equals e to the x, the slope at the point a, f of a, is equal to f of a, is equal to the y value. This means that the derivative at a is equal to f of a. The slope at a is equal to the y value at a. That ends up being something that's very useful in mathematics, because we get this. For this particular function, f of x equals e to the x, the derivative at every point x is the original function. F prime of a is equal to a, and that works for all x's, for all a values. Therefore, f prime of x is equal to f of x. Or said another way, the derivative of e to the x is equal to, right, the derivative of e to the x is equal to the original function, e to the x. It is its own derivative, and that makes it quite useful. One note here, this is not the power rule. Note, this is not the power rule. All right, go back to power rule. Power rule says the derivative of x to the power of n. In the power rule, the base is the variable. The base is the variable. That's when you use the power rule. For the exponential, such as e to the x, the exponent is the variable. And I know that you know that, but just be careful because students often, just in their getting used to using the power rule, try to use the power rule on any exponential function, and it doesn't work, right? The derivative of e to the x, we don't bring down the x and make it e to the x minus 1, right? That is no. We cannot use the power rule on an exponential. We can only use the power rule when the base is a variable and the exponent is a number. Okay, so we're not using the power rule here, and we note that we have a new rule for the derivative, that the derivative of this e to the x function, this exponential function with base e, is equal to e to the x. You might be asking, what about if it's base 3 or base 7 or some other base? And we'll talk more about that later. The answer is similar, but none of those, if the base is not e, none of those have a derivative that is exactly the same as its original function. That is what makes e to the x, that number e, unique. Okay, let's try an example. Let's try a function such as f of x equals, let's go with 2 square root of x plus 3 e to the x. And let's say I want to know what is the derivative here. Okay, so f prime of x. Before I do that, let's rewrite 2 square root of x as 2x to the 1/2, is that rational exponent, plus 3e to the x. And now let's take the derivative with the 2x to the 1/2, right? That we will use the power rule. Power rule. With the 3e to the x, we're going to use the fact that the derivative of e to the x is itself e to the x. Okay, so two different rules here within this one problem. For the power rule, we have the 2. We'll bring down the 1/2. It'll be x to the 1/2 minus 1. That's negative 1/2. Power rule. Plus 3 times, the coefficient just stays there, the derivative of e to the x. But the derivative of e to the x is simply itself e to the x. So the derivative of 3e to the x is 3e to the x. Simplifying here, 2 times 1/2 is 1, so I get x to the negative 1/2 plus 3e to the x, which is a fine answer, like that answer. Or you could write that as 1 over the square root of x plus 3e to the x. There you go. That's how we take the derivative of e to the x.